Okay, we are talking about part two of RGB material. So basically, rigid gas permeable lenses are those lenses we made material made by made which permeable to oxygen, and they have inherently rigid similarity with PMMA. Yes, PMMA is basically came earlier than uh, current rigid permeable gas lenses. So, but due to the oxygen permeability, have become popular by semi-soft lens sometimes, but it's not good name. And made up of uh, polymers, example silicons and polystyrene. So let's move further. So rigid lenses are able to replace natural shape of the cornea with a new refracting surface. Yes, contact lens or does that work, but definitely we have to take into account about the tear lenses. A regular spherical rigid contact lenses can provide good level of vision in people who have astigmatism and distorted corneal shape is with keratoconus. And this RGB is corneal lens. RGB is a material actually. RGB is a material, I think you know. When it lands to cornea, it is corneal lens. Whenever it lands to sclera, it is scleral lens. A partially land in cornea and partially land in the sclera is called semi-scleral lens. Yeah, it's or mini scleral sometimes. But yes, there is a guideline for the nomenclature currently. So significant milestone of the contemporary history of the contact lens development. So first, 1940s PMMA came. Okay, that's a hard lens, rigid lens, not rigid gas permeable. PMMA we don't call PMMA. RGP we call PMMA only hard lens. Okay, in 1970s HEMA hydrogel is developed, and after that in 1980s the development of RGB material is there. Okay, and obviously we know the dominance of market by silicon hydrogel in 1999. Yeah. So ideal material property. What are the ideal material property? First and foremost, we want oxygen to be transferred through that material. Weightability, transmissibility, specific gravity, hardness, scratch resistance, and flexure. PMMA has all these good qualities except oxygen permeability. So PMMA is actually really good material, but except oxygen transmissibility. And if there is no oxygen transmissibility, there will be hypoxia and there will be accumulation of lactic acid. There will be what we call osmotic imbalance, and there will be definitely edema and a lot of other changes. Yes, on endothelium cell dies and polymegathism, and there are a lot of things that goes wrong. And oxygen transmissibility is central important uh, characteristics of that particular material. So that's why PMMA we avoid it, like it's almost 0%. Yes, the use of PMMA. So RGB material, definitely it's not PMMA is not a RGB material, but yes, then after CAB cellulose acetate butyrate, and then after T-butyrate and currently silicon acrylate, fluorosilicon acrylate, and polyfluoroether. These are all materials. Currently, three materials are used, and these are historical purpose. These three, okay, the historical purpose. So, for historical purpose, let me summarize it for you. It will be helpful. So, for PMMA, oxygen permeability is 0. Yes. For CAB, you know CAB, full form of CAB, cellulose acetate butyrate. Okay. For CAB, very low, and butylstyrene, moderate to low. So flexibility of PMM is very hard, it's very rigid. CAB is slightly more flexible, yes, moderate comfort as compared to PMMA, and butyrate is more flexible as compared to CAB. So surface wettability poor and hydrophobic in PMMA, but better than PMMA in CAB and moderate in butyrate. Advantages are excellent optical clarity and surface smoothness in PMMA. CAB slightly better comfort and weighting than PMMA. So because the surface wettability is better than PMMA in CAB. In butyl styrene, flexibility reduces lens awareness and moderate comfort. Okay. So disadvantage of CAB is no oxygen transmissibility, poor comfort. One, and disadvantage of CAB is still low oxygen permeability, very low, like 4 or 8 decay. Yeah, so let's limited modern use. And butyl styrene, it low oxygen permeability, it's still very low. Okay, it's compared to today's GP. So I have talked about this slide because I think it's useful for the historical purpose. You must know what are the materials. So first PMM is there, then CAV is made, I think, then uh, butyl styrene in that fashion. I think so. Okay. So RGB material has a component. So basically monomers are added to make more polymers. Make polymers. What are the monomer? Place the percentage of monomer affected by either oxygen permeability, rigidity, instability, and wettability. We would definitely want all of three characteristics in a material. So what are the three things that are there in? So if silicon is more added in the material, the more flexible bond are greater oxygen permeability. Basically, silicon oxygen silicon bond has a more flexible bond angle and greater oxygen permeability is there through diffusion. But hydrophobic material very soft and so very stable because of the silicon is definitely hydrophobic. It will create hydrophobic material and it is very soft and not very stable, so can be warped and flex because if you add too much of silicon. So these are the benefit of adding too much of silicon, and at the same time what are the disadvantages of adding too much of silicon. Too much of silicon means hydrophobic. Too much of silicon means very soft and not very stable material, because RGB, we want RGB to be stable, yes, because we want tear film to be there, tear, not tear film but tear lens to be there, yes. So these are the modern material that we are going to discuss: silicon acrylate, fluorosilicon acrylate, and then perfluoroether. Yes, so silicon acrylate is GP Lens's first successful GP material with silicon acrylate composition, also called silicon methacrylate. That's a name. Yes, you understand. Silicon is present. Silicon's side chain on the main carbon and carbon polymer chain, and silicon side branch increases the volume and allow the oxygen pass. Basically, silicon is responsible for the volume of oxygen pass. Silicon will increase decay. Yeah, yes. So even silicon hydrogel, that's the case. So introduction of 1979, major breakthrough of oxygen permeability compared to, so this is introduced in this time, and the major oxygen permeability is compared to PMM, because PMM is almost zero. Yes. Silicon acrylate polymer contains silicon methacrylate, the main oxygen permeability component. So basically, silicon methacrylate is main oxygen permeability. Wetting angle, so counteract hydrophobicity and enhance the surface wettability. So basically, there is some surface wettability to cross-linking agent, which increase what? Which increase rigidity. Whenever we do cross-linking, which increase rigidity. But at the same time, if you do too much of cross-linking, it will reduce decay by T. If cross-linking is too much, yeah. So, and hydrophobicity of silicon can attract lipid and protein deposition. It's always there, even in silicon hydrogel contact lens, hydrogel contact lens. Yes, too much of hydrophobicity will increase lipid deposits. Yeah, definitely protein too, but too much of ionic surface ionicity will increase protein deposits. It's always there, but yes, too much of hydrophobicity will create lipid deposition. And redness, dryness, and fluctuation vision is there. Rapid tear film drying on the surface, which is definitely because of silicon hydrophobic nature. Higher the decay, silicon acrylate material may also lead to surface deposit, warps, and cracks. This much you must understand. We want this higher decay, but at the same time, whenever we increase silicon content, we must understand there is surface deposition, warpage, and crazing and brittleness would come along with the silicon. Yes, that's the basic concept here. So silicon acrylate in the era of successful material in original silicon acrylate material in late, as we know. The PMMA backbone gives the material dominant physical property, especially rigidity, and silicon oxygen silicon bond is flexible and extensible, and the result is significantly increase in oxygen permeability but reduce material rigidity. So increase in silicon will definitely reduce the rigidity, but at the same time increases the oxygen permeability. As I have told earlier, silicon oxygen silicon bond is responsible for the higher oxygen permeability. Just remember this term, it's very important. Why it's important when you add silicon? Because of this bond, the structural integrity of that bond, the basically the length of and distance between silicon and oxygen and the angle it forms so that oxygen can pass from that. Okay, so it's very important that you understand silicon oxygen silicon bond is responsible for increasing oxygen permeability. So decay is approximately 12 to 60, which is a good, isn't it? Greater than 24, Holden-Mutz criteria. If greater than 24, it can be used daily use. Yes. A wetting agent may be incorporated to enhance the wettability, usually methyl acrylic acid. So it is done in even soft contactants. Yes. So wetting agent is there. So material chemistry results in a net negative charge on the surface, especially if methyl acrylic acid is used as a wetting agent. So methyl acrylic acid is used, then what happens? So charge, net negative charge on the surface. If it is net negative charge on the surface, what happens then? Surface is negatively charged, so that protein deposition will increase because lysosome is positively charged at 7.4 pH. Yes, yeah, lysosome is neutral when pH is 11. Yes, almost 11. So that's the concept basically. So methyl acrylic acid is being added for the wettability. At the same time, being added methyl acrylic acid will create surface charge complete negative, and negative surface charge will attract positive proteins, especially lysozymes, and entire lysozymes is in abundant. So that's why negatively charged surface will pull protein. At the same time, hydrophobic surfaces like adding silicon will attract lipids. Majority, just saying majority. I'm not saying that this contact lens with particularly surface charge will not attract uh, lipid, but yes, majority it will attract uh, protein. But at the same time, if surface is not hydrated, it will attract lipid. So these are the some materials. Just I'm taking this slide just for your reference, and again taking this slide from the book. Just see what happens. These are some materials name and manufacturer's name. Just pause the video and you can see. Okay, this decay, and there are things. So what are the advantages and disadvantages of silicon acrylic? We have already talked about it, but let's go ahead. Wide range of material available, yes. Wide range of design with a practitioner control. Low to medium decay available. Good dimensional stability, yes. Good vision with a limited lens flexure. Good scratch resistance. But at the same time, attract protein from the tears because of methyl acrylic. Some materials are brittle and with the breakage a problem, yes. The high incidence of 9 o'clock staining in some indicates CLIPC. Okay, let's move further. Fluorosilicon acrylic. What happens? We add fluorine in silicon acrylic. Okay, that's the concept. So fluorosilicon material will develop as a result of effort to further increase decay. That's main point. You will be asked in Viva. Okay, just remember why people add fluorine in silicon acrylic. Just answer it because uh, we want to increase the decay of that material because fluorine will definitely increase decay. Okay, so why is it the effort to further increase the decay of rigid material and increase resistance to the surface deposits? That's another point. Okay, so fluorine is added on the base of silicon acrylic. See, we have already silicon acrylic, and fluorine is added on the base of silicon acrylic. So basically, what are the purpose of silicon adding fluorine is to enhance the oxygen permeability. So lower surface charge. It will also help in lowering surface charge so that deposition there is deposition resistance, and DKC ranges pick up, yeah, from 40 to 100 or more is achievable. Decay are high enough for extended wear, yes, greater than 87. It just yes for at least Holden-Mutz criteria, and decays are high enough for extended wear to be possibility. So fluorosilicon acrylic is generally more flexible than silicon acrylic. Let me tell you one thing which is I think important in your life. Greater the decay of the material, more the softer of that material goes, or greater the decay of the material, lesser the modulus of elasticity. Okay, so greater the decay, softer the material becomes. It's always there, it's always there. Okay, okay, not so in soft contact lens but definitely in rigid contact lens. It's like the grosser rule of thumb. Just remember this. Surfaces are relatively scratched. Okay, it's also there. The more the decay, surface is relatively scratched. The more the decay, another point, the lesser the lifetime of contact lens. It's also there. Yes, especially in rigid contact lens. Higher the decay, lifetime of the contact lens goes down. It's also there because material decays faster. Not decay faster, but decays faster. Yes, it will degenerate faster. Fine. These are the some materials. Just pause the video and see what are these materials. Are like fluorochrome, for example, and others are here, and other higher decay value is low decay value fluorosilicon. See higher decay value. I think Paragon. I have practiced this material, and is there anyone? I think Boston CO. We have practiced this material. Yes, so there are common material which is minigun. Definitely, we have practiced this material. It's very good material. So just see decay is so much higher, which is very good, isn't it? Yeah. Just pause the video and see. So what are the advantages of fluorosilicon acrylic? What are the disadvantages? Let's talk about it. The main advantages is definitely higher decay. Suitable for flexible extended wear. Yes, it's got beyond 87. Then we can think about extended wear. Better weightability. Poor deposit problems, as I've already talked, and lower incidence of CLPC, papillary conjunctivitis, basically. So basically, and modification is possible, but disadvantage brittle and if too thin. Yes, require careful manufacture. Dimension established depend on the manufacturer material and corneal adhesion in some cases. But yes, definitely, we cannot make it too thin. Definitely, we have to be cautious on manufacturing high decay material. It's always there. Whenever the decay material of the decay goes high, it's better that dimensional stability. We have to think a lot about these things. Yes, because material is brittle. Material is not just brittle. They are having less modulus of elasticity. So last thing, the perfluoroether. What is a perfluoroether? Perfluoroether lens is a novel and the distinct material category. Perfluoroether consists of fluorine, oxygen, carbon, hydrogen. Just remember perfluoroether. Okay. So composition of perfluoroether. Perfluoroether material are fluorinated polymer that incorporate ether linkage with a polymer chain and resulting in a structure that impacts specific chemical and physical property. So oxygen permeability of the material exhibit higher oxygen transmissibility. It's very high in perfluoroether and facilitated better corneal health compared to traditional RGB material. But yes, fluorosilicon acrylic is also good. Surface chemistry. The surface characteristic of perfluoroether material contribute to their weightability and resistance to protein and lipid deposition, enhancing lens comfort and reducing maintenance needs. So basically, it also has very good characteristics, protein and lipid deposition resistance, which is very good, and also very good weightability. So advantage of perfluoroether is higher to oxygen transmissibility. That's main advantage. Perfluoroether allows more oxygen rich and cornea promote definitely health, enhance weightability, comfort, resistance to deposit. We really want that particular thing. Durability. Perfluoroether is robust and can withstand rigorous in daily use and offer longevity compared to other materials. So being all these things at the same time, durability of perfluoroether is also good. That's very good. What are the disadvantages? Cost, definitely. Advanced material processing and material contribute to the higher cost. It's always there. Refractive index. So compared to other material, perfluoroether lens have lower refractive index, and lower the refractive index, we need thicker the lens. Yes, simply. So limited availability due to the specialized nature. Perfluoroether lenses may not be widely available as other lenses, especially fluorosilicon acrylic, which is commonly available. So let's discuss these three things in one by one. Okay, silicon acrylate, fluorosilicon acrylate, and perfluoroethers. So chemistry: silicon segment and acrylic bond in silicon acrylate. At the same time, fluorosilicon acrylate. Yes, we add fluorine to silicon acrylate. Perfluoride heavily fluorinated ether chain. It's very important. You must understand heavily fluorinated. Okay. Here we add fluorine, but here is heavily fluorinated. So oxygen probability moderate to high. We know 40 to 100 or almost 40. I think yes, something 40 to 60 or yeah, from 100 above, 40 to 100 above, and it's even higher. So mechanical modulus. So basically stiffer silicon acrylate, moderate balance fluorescent acrylate. It's very variable, basically engineered, because cross-linking chain is there. So durability of the chemical stability good, but silicon can be cracks. Basically, silicon can crack, but definitely fluorosilicon better than silicon acrylate, and excellent chemical resistance and durability in perfluoroether, and it's again depend upon the chemical chain and reactions. Okay, so basically cross-linkings. Need for surface treatment and coating? Usually yes, in case of silicon acrylate. Often yes, but better, easier to wet by fluorosilicon acrylate. Usually yes, and it's in case of surface treatment, it's basically I am definitely going to talk about in next two slides. But yes, surface treatments are always there. In case of RGB, yeah, it's better. Yes, not coating but better. So let's talk about other product wettability for tear film spread. So basically, what is wettability and or tear film? So moderate to poor, better with silicon acrylate, better than silicon acrylate, and often low hydrophobic, needs sweet treatment. So often perfluoroether is treated. Yes, lipid and protein deposition, more lipid deposition in silicon because of silicon. Reduced deposition versus silicon in compared to silicon acrylate, fluorosilicon acrylate, less deposits, and lowest lipid deposits in perfluoroether. So water interaction, low wettability can be reduce comfort. Obviously, if there is a low wettability, it will reduce comfort in silicon acrylate. So fluorosilicon acrylate improve tear interaction, and perfluoroether least interactive. So unless treated, it's very important. Least interactive unless treated. That's why surface treatment is very important.